students might have forgotten because of that long delay or long gap. Okay, now let me first show you that file. There was a gap. I don't know whether you remember what we discussed in our last class. It's quite a long time back, some 10 days back maybe. Okay, so something will come now on your screen. Is it coming now?
Yes, sir.
Good. So now you remember that we were discussing charge simulation method formulation, and we discussed about the single dielectric case. So again, I just go back. Yeah, this one was our example. That this is an electrode. So what we did, we tried to simulate the effect of the actual charges which are present on the surface of the electrode. But where the charges are and how much charges are on the surface is very difficult to tell. So we are putting some fictitious charges inside the electrode, and for every fictitious charge we are putting one point on the surface, and we are saying that the effect of the actual charges on the surface will be simulated by the effect of the fictitious charges. So then what we will do, we'll compute the field by the cumulative effect of the fictitious charges and not by considering the actual charges. This is the concept of charge simulation method. Now, why we took the charges inside the electrode? The reason was that our region of interest was outside the electrode. Now, if I put these charges outside the electrode, then the charges become located inside the region of interest. Then we want to know the field at that particular location because it is within my region of interest. However, we find that the distance between the charge and the point becomes zero because charge is exactly located on that particular point, which means we cannot compute the field at that location of the charge. So if there are a number of charges, a number of points outside the electrode, we will not be able to get the results if the charges are placed outside the electrode. Now, any system where we don't get the solution at any particular point, these are called points of singularity. And any system that gives rise to point of singularity is not a very good system or a good method. So, we don't put the charges outside the electrode, but we put the charges inside the electrode. The issue becomes complicated where, right, now here you see, it's a multi-dielectric arrangement. On the top, you have the electrode. Its potential is V. So what we are doing, we are putting some fictitious charges inside the electrode. And for every fictitious charge, one particular point on the electrode surface. But then there are two dielectrics. So there is a dielectric interface. And as a result, there will be some charges on this interface because of the dissimilarity of the dielectric constant of the two materials. But the problem that we are going to face is that both sides, that is left side as well as right side of the dielectric interface, is my region of interest. So, irrespective of whether I put the charge on the dielectric A side or you put the charge on the dielectric B side, it will be in the region of interest. So how do I avoid point of singularity? For that, the proposal or the methodology is that for every point on the dielectric interface, we are not going to take one charge, as in the case of electrode, but two charges. One set of charge on the dielectric A side, another set of charge on the dielectric B side. And our methodology is that whenever we are computing the field for dielectric A, we will not consider the charges which are placed in dielectric A. That means here you can see that that as my mouse is moving, these charges will not be considered when we'll compute the field for dielectric A. And similarly, these charges on the right will not be considered when we compute the field for dielectric B. Well, then how do we do it? Well, for that, let me explain it very clearly. First, we will have to number the charges and the points. So what we are doing, we are saying that there are total n1 number of charges inside the electrode. Fine. But then for every charge, there is a point on the electrode. But we can clearly see that some points on the electrode are on dielectric A side, on the left, and some points on the electrode are in dielectric B side, on the right. So we are subdividing these numbers. We are saying that 1 to NA is the number of charges and the points which are on the dielectric A side. And Na plus 1 to N1 are the number of charges and the points which are on the dielectric B side. Please remember that all the charges and the points are sequentially numbered. So, if there are N2 number of points on the dielectric interface, their numbering will start from N1 plus 1, because up to N1 is within the electrode. So now it will be N1 plus 1 to N1 plus N2. This is the numbering of the points. But then we will have two sets of charges. So the charge numbering will be on the dielectric A side, it will be N1 plus 1 to N1 plus N2. On the dielectric B side, it will be N1 plus N2 plus 1. That means where we have ended on the dielectric A side. So N1 plus N2 plus 1 to N1 plus 2N2. So that is the numbering system that we are going to follow. Now we are going to write the equation. How we will write the equation? First of all, we are going to write the equation on the electrode. We are going to say that the combined effect of the charges for a point on the electrode is such that its potential will be equal to the known potential, that means V. Now let's say there is a point on the left hand side on the electrode on the top, which is in the dielectric A side. When we are going to compute the field for this point, which are the charges that we have to take? The answer is 1 to N1. That means all the charges within the electrode, because they are outside the region of interest, and not the charges within N1, but within dielectric B side, not the charges within dielectric A side. So 1 to N1, that's on the top, and on the right, N1 plus N2 plus 1 to N1 plus 2N2. So this will be applied to the point on the electrode on the left. So that's what it is written here, equation 16.10. You can see here Pijqj, which I have already explained in my last class, Eijqj is Eij is the potential at the location of ith point due to unit charge at the jth point, multiplied by the charge magnitude at the jth point. So we are taking j is equal to 1 to n1, which means j is equal to 1 to n1 means all the charges within the electrode. And then we are taking j is equal to, you can see 16.10, n1 plus n2 plus 1 to n1 plus 2n2. That means the charges on the right side, that is in the dielectric B side on the interface. Because this point is on the dielectric A side on the electrode. So how many such points are there? From the figure we find 1 to Na. So therefore, this equation 16.10 will be applicable for I varying from 1 to Na. Then what about I varying from Na plus 1 to N1? Yes, it will be almost similar. Only thing is that now the points are located on the dielectric B side. So we will not take the charges located in the dielectric B, we will take the charges located in dielectric A. Therefore, we have equation 16.11. You can see here j is equal to 1 to n1. Then j is equal to n1 plus 1 to n1 plus n2. Look at this here, the charges on the interface which are located on dielectric A side, they are numbered n1 plus 1 to n1 plus n2. That's what exactly 16.11, left hand side delay. And the summation is equal to the known electrode potential. And this will be applicable to how many points? Na plus 1 to n1. So here you can see 16.11, I varying from Na plus 1 to n1. So therefore, when I apply this condition of known potential on the electrode boundary to how many points? In one number of points. There are in one number of points on the electrode boundary. So from 16.10 and 16.11, I get in one number of equations. But our total number of variables here, you can see that it is in one number of charges inside the electrode, then 2 n2 number of charges for the interface. Because total number of points is n2, so there will be 2 n2 number of charges. So it is n1 plus 2 n2. And to solve for that, we need n1 plus 2 n2 number of equations. How do I get it? So now we come to the dielectric interface. We take a point. Since it is on the interface, I can take this point to be located in dielectric A or in dielectric B. So we calculate the potential of any point, considering it as located in dielectric A or dielectric B. So we use the same equation 16.10, which is for a point located in dielectric A, and 16.11, which is for a point located on dielectric B. But here I is same for both the equations. And therefore, when I say that this point is a unique point on the interface, the potential must be unique. So what we do is we take the left-hand side of equation 16.10 is equal to the left-hand side of equation 16.11, where I varies from n1 plus 1 to n1 plus n2. That means on the dielectric interface. When I do that, then I see that the first term of the equation, they are common. So they will cancel. If this left-hand side of 16.10 is equal to left-hand side of 16.11, if you write that equation, then they will cancel. So what will remain is only the second term. So this is exactly what we can see here, where from the right-hand side, we have brought it to left-hand side, we have made right-hand side 0. So what we are getting, this is called potential continuity condition. That means the potential on the dielectric interface must be continuous irrespective of its location. So we get this. But then how many equations I get? I get n1 plus 1 to n1 plus n2. That means n2 number of equations. So 16.10 and 16.11, I get n1 number of equations. 16.12, I get n2 number of equations. Still, I need n2 number of equations because total number of variables is n1 plus 2 n2. So we go to the next boundary condition, that is the normal component of flux density. That is typically the Laplace's equation condition. I have taken here right hand side is 0, that is dNA minus dNB is 0. If it is equal to charge density, it becomes the Poissonian condition. And this is applicable to a point on the dielectric interface. So how many points? N1 plus 1 to N1 plus N2. So if I apply this boundary condition, I will get N2 number of equations. So then 16.10, 16.11, I will get N1 equation, 16.12, I will get N2 equation, 16.13, I will get N2 equation. Total N1 plus N2, 2 N2 equations. So that's what we need. How do I get dNA and dNB? It's very simple. We take the, we don't take Pij here, we take the field intensity component, that is the first order derivative of potential coefficient, and then multiply it by epsilon to get the d. So this is exactly like, this left hand side of 16.10, take the first order derivative and then multiply it by epsilon a, you will get the dNA. Take the left hand side of 16.11, it's for dielectric B, and take the first order derivative, multiply it by epsilon b, you will get dNB. So then dNA minus dNB is equal to 0. You can do this arithmetic or algebra, whatever you turn it. So you will arrive at 16.14. Please practice it on a white paper. Although it looks very complicated, but practically it is not that complicated if you understand it clearly. So if I look at it now, if I write it in a matrix form, it is a square matrix. So it will be an n by n matrix. Sorry, not n. N is equal to n1 plus 2n2. Now, if I look at the number of rows, 16.10 and 16.11, it gives me n1 number of rows. Out of that, the first one gives na number of rows and second one gives another set of rows. So here you can see I have subdivided it. The first set of rows 1 to na, second set of rows na plus 1 to n1, third set of rows n1 to n1 plus n2, fourth set of rows n1 plus n2 plus 1 to 2n2. Similarly, the columns. If I do that, and if I look at 16.10, if I look at the j, I will see that j is equal to 1 to n1. All these Pij's are present. So here you can see on the column side, 1 to n1, Pij is present. But if you look at 16.10, j is equal to n1 plus 1 to n1 plus n2 is absent. I repeat, j is equal to n1 plus 1 to n1 plus n2 is absent. So in the matrix, you see in the first set of rows, the second set of column is 0 because there is no coefficient. But the third part is present from n1 plus n2 plus 1 to n1 plus 2 n2. So you can see the third part is present. In this way, 16.11, I find that j is equal to 1 to n1 is present. So in the second row, second set of rows, you see the j is equal to 1 to n1 is present. Then n1 plus 1 to n1 plus n2, that is also present. So here you see second row, set of rows, n1 plus 1 to n1 plus n2, Pij is present. But you can see here 16.11, the third set is not present. That is n1 plus n2 plus 1 to n1 plus 2 n2. So you see the third set is 0. In this way, if I look at 16.12, I find that j is equal to 1 to n1 is absent. So the third set of row, the 1 to n1, it is 0. But then n1 plus 1 to n1 plus n2 is present. So you see this is Pij, present, second set of column. Then third set of column, n1 plus n2 plus 1 to n1 plus n2. Sorry, this is to be 2n2. There's a mistake here. This is minus Pij. So this is minus Pij. And in equation 16.14, all the terms are present. So the first term is epsilon a minus epsilon b into Fnij. This is for j is equal to 1 to n1. Again, if you look at it, epsilon a minus epsilon b into Fnij, that's exactly the first set of columns. Then second one is minus epsilon b into Fnij, which is n1 plus 1 to n1 plus n2. So this is the second set of columns. And third one is epsilon a into Fnij. That is n1 plus n2 plus 1 to n1 plus 2n2. That's the third set of columns. So this is exactly the coefficient matrix for multi-dielectric arrangement. So it is not 100% full matrix, but still you can see there are only small segments of this matrix, which is 0, rest are all occupied. That means rest coefficients are non-zero. So charge simulation matrix, which is for single dielectric, is fully occupied. But in multi-dielectric, it is not fully occupied, but on an average, it is 70 to 80% occupied. Types of fictitious charges I have considered in my last class. I have sent you some diagrams, how the charges are placed. I hope you have gone through it. Now the accuracy criteria. See, any simulation, don't think that anything that a computer program does is correct. Computer is as intelligent as the person using it. That's what the old proverb says. Now you can talk about machine learning, etc., but still finally it is the programmers who matters. So typically it is called computer. I'll jokingly say that in management there are a lot of systems that first in, first out, last in, first out, something like that. These are typically done for logistics. Nowadays, logistics is a very, very big issue. For example, say when you travel, you take a suitcase. The clothes that you put at the first, that goes at the bottom. So you cannot take it out first. The clothes that you put on the last, that is always on the top. So you take it out first. This is called last in, first out. Similarly, there are many such systems like first in, first out, etc. That is typically used by these all logistics companies. I jokingly say that computer is called garbage in, garbage out system. That means if you feed garbage data to the computer will give back garbage data to you. So it is very, very important to understand that you are handling the computer correctly. So how do I know that my simulation is accurate? So for that, what we do, we find potential error on the electrode at a number of control points. Now the issue is, what is a control point? Control point is something like, here. See, you can see that there are 2 points on the say 2 successive points on the electrode surface. So I take a point midway between these 2 points, and that becomes my control point. So after the solution, I take the combined effect of all the charges at the control point, which is also on the electrode surface, and compute the potential. And it should also be equal to the electrode potential. But it will never be the same. That means if the electrode potential 100, you will never find 100. You might find 19.9, you might find 100.1. So that's called the potential error, the difference between the computed potential and the actual potential or the true potential. So all the errors we compute at the control points, never at the contour points where we have solved the problem. So this is first the potential error on the electrode, but that's not the best judge. We know that in field theory there is a very well-known condition that if you have an equipotential surface, flux lines, they are always at 90 degrees to the equipotential surface. We apply that knowledge here. That means we calculate the components of electric field intensity at the control point and they then find out the normal component. Normal direction is 90 degrees, so I find out how much is the angular deviation from 90 degrees. This is a very stringent condition of accuracy check. I have seen that even if the potential error was 0.01%, that means if the actual value is 100, I was getting 99.99, but still deviation angle was more than 1 degree. So deviation angle is a very, very stringent condition, and the reason is very simple, because deviation angle comes from field intensity, which is the first order derivative of potential. And if you recall your knowledge of numerical computation, it is always stated that if you integrate a variable, whatever is the error in the original variable, that will be reduced after the integration. And if you differentiate a variable, whatever is the error in the variable before differentiation, it will be increased after differentiation. Since deviation angle is first order derivative of potential, so it will be always more than the potential error. So that's a much more stringent check for accuracy. We do the same thing for the dielectric surface. Basically, we check the potential discrepancy first. That means first we consider the one point, the control point, to be on the dielectric A side. So we ignore the effect of those charges which are on dielectric A and take all the other charges and compute the potential. Then I consider the same point on the dielectric B and we ignore the effect of the charges in dielectric B. And we take all the other charges and compute the electric potential at the control point. But since it is a single point, the potential should be same. Again, it will never be same. So we call it potential discrepancy. We can also go through the normal component of flux density. That error also, that means we can compute dNA, that means normal component of flux density from dielectric A side and also from dielectric B side at the control point on the dielectric interface. And then see how much is the deviation. So after checking all of that, if we are satisfied, then only we say that our simulation is good. But then if the simulation is not good, then what we do? So for that, we have to know that what are the factors that affect simulation accuracy. Well, two factors are quite obviously that affect. One is the type of the charges that we have used, type of the fictitious charges, and secondly, the number of fictitious charges. Typically, if you increase the number of fictitious charges, the error will go down. But it will not go down infinitely. That means it will not become zero. There is always a saturation level. That means If you increase the charge from 100 to 200, 200 to 2000, you will see that after a certain limit, the error is becoming almost constant. For that, there is another factor that we'll have to take, that is the location of the charges. So how do we do that? That is by this one. Here you can see that this solid line is the electrode surface, let's say. Then there are two contour points on the surface, and the distance between them is, let's say, A1. And then for any contour point and its corresponding charge, let's say the distance is A2. So then the ratio of these two, that is A2 by A1, I am saying this is lambda. This is called assignment factor. Here you can see assignment factor. So we compute the assignment factor. So Steinbegler in its original paper proposed that this factor should be 1 between 1 and 2, while many other researchers later on have suggested that it should be between 0.7 and 1.5. So these are all the several aspects. So if you work on it, slowly you learn. It's not that in one day one can learn everything. So slowly we learn the intricacies of all the methods. A solution of system of equation in CSM, well, that's very straightforward, because in this case our coefficient matrix is almost full, or maybe 70% full, so we don't go for the iterative solution. Rather, we go for a direct method like Gaussian elimination, or maybe the lower LU decomposition, lower upper decomposition. So that will give quite good results. Only thing is that we have to check the conditioning of the matrix. If the matrix conditioning is bad, then we can go for the iterative methods like Gaussian. So these are all part of the numerical techniques. That's what I think I have for you for this particular topic. So I close this topic, and of course we will get the notes. I move on to another topic now, which is for you is known, but still I want to repeat it for your knowledge, because this is something which is practically also relevant. I hope you will see this now soon. Is it coming? Now this is called utilization factor. So we call it field utilization factor. Now this is to some extent not very rigorously analytical, but quite okay with practical applications. We take this ratio as average stress by maximum stress. Now you can always ask, what is average stress and what is maximum stress? Well, maximum stress, we have no issue. Whatever the point in the system where stress is maximum is the maximum stress. Then what is the average stress? Well, average stress, for that we have a formula. That means, what is the potential difference? Let's, for example, in this minimum distance, that is x, so average stress will be 2v by x. So the formula is potential difference divided by the minimum distance. That's the formula. I mean, just we have to accept it in that way. And if we take average stress by maximum stress, we will get this utilization factor. In all practical cases, the average stresses will be less than maximum stress, so this U will be less than 1. If it is uniform field, that means if the field stresses are the same everywhere, then of course this U will be 1. And for a highly non-uniform field, this U will be quite lower than 1. Now you can understand that why we use this, that this U is nothing but a measure of non-uniformity of the field. If its value is very low, then the field is highly non-uniform. And if it is 1, the field is uniform, or it is very close to 1, it is quasi-uniform. For example, here there is an electrode and earth. So average stress will be very simple, that potential of the surface divided by this minimum distance. Similarly, maximum stress we can find that will be not at this minimum distance point. Why? Because at the outer point, the flux concentration will be much higher because of the bending of flux rate. So here the maximum stress will come at point A, and that stress will become the maximum. Anyway, and in some literature, by the way, there is something called field factor, which is just the reciprocal of the utilization factor. That means here we take the ratio as E max by E average. Just two very plain and simple analytical expressions of how we get the field factor or utilization factor. Let's say the case of concentric spheres. This is something which is a very basic field theory configuration. There is an inner sphere having a potential V. There is an outer sphere which is R. So at any radius x from the center, if the charge on the inner sphere is Q, then at any radius x, you can see the field intensity will be given by Q by 4 pi x square. This is very well known for spherical system. So, what is the potential difference between the two electrodes? Of course, integration of E dx. So we do the in E dx, and actually it is from minus E dx, where we move from zero potential to higher potential. But this integration you can see is from small r to capital R. That means from higher potential to lower potential. That's why that minus sign is not used. But I should have said that to be very precise, we should have taken this integral from capital R to small r, and with a minus sign. And if we do that, then we see that V is equal to this expression, 1 by R, small r minus 1 by capital R. So from that, what we can see, we can get a value of Q by 4 pi epsilon. Now, what is the significance of this expression? This gives us the amount of charge on the inner sphere. Because on the right hand side, V is the potential, small r and capital R are the dimensions which we can measure. Epsilon is the permittivity which you can measure. So from this we can get how much will be the charge on the inner sphere. And then from this expression of field intensity at any distance x, we can see that the highest value of field intensity will take place for the minimum value of x. What is the minimum value of x? That is x is equal to r. That is the diameter radius of the inner sphere. You cannot go inside the inner sphere. So E max is Q by 4 pi epsilon r square. And therefore we get an expression for E max. And E average, what is the potential difference? It is V. What is the minimum distance between the two electrodes? That is capital R minus small r. So you can see here, E average, here you can see E average is V potential difference divided by capital R minus small r. And this is the E max. So therefore, E average by E max is small r by capital R. So you can clearly see that it will be always non-uniform because small r is less than capital R. And you can clearly see what will be this. And what about the capacitance of the system? Obviously, C is Q by V. And from this one, I can clearly get an expression for Q by V. So I get the capacitance of the system. We extend this discussion for concentric cylinders. another theoretical aspect, but this is also equivalent to our cables. So it's, drawing wise it is same because this is the cross-sectional plane. We have the inner cylinder of radius r, we have the outer cylinder of radius capital R. Potential of inner cylinder is V, the outer cylinder is R. So at any radius x, E is given as Q by 2 pi epsilon x, where Q is the charge per unit length on the inner cylinder. Since it is a cylindrical system, charge should be always taken as per unit length. Why Q by 2 pi epsilon x? Because D, the flux density, will be charged by surface area. And what is the surface area? 2 pi x multiplied by 1. 1 is the length. 2 pi RL is the surface area of the cylinder. So 2 pi x into L is 1. That is D, and then epsilon brings in to make it E. So then we integrate to get the potential difference between the two cylinders, and that's what we get. So again, I get this expression for Q by 2 pi epsilon, from where we can get how much will be the charge. Similarly, maximum field intensity will occur on the inner cylinder surface, that is x is equal to R. So Emax is Q by 2 pi epsilon R, and Q by 2 pi epsilon you have got, so you get an expression. What is E average, which is same, that is potential difference is V, minimum distance is capital R minus small r, so this is E average. So U is E average by Emax, so you can see. So U is a function of capital R by small r or small r by capital R, whatever you can say. And what about the capacitance of the systems? It's the same, that C is Q by V. So from here I can get, but here capacitance will come as capacitance per unit length because it is a cylindrical system. So if it is farad per meter or microfarad per kilometer, typically we use it as microfarad per kilometer for the cables. That is a more practical unit of such capacitance. Now this is a very typical, sort of discussion. Doesn't go into all those detailed formulations, but yes, in many practical applications we do use such formulations. So I think today I will close here, because in my next class I will start a different topic, and my next class is tomorrow 11 o'clock. That's it, right? Okay. So I think then we close today. Okay, you can log off now.
Thank you, sir.